Okay, now we continue on the capacity and sizing of control valve. Okay, this obey-attainment I already explained before inside the previous subtopic. Okay, so basically for the valve, to regulate the flow in the valve, the flow capacity of the control valve would varies from 0 when the valve is closed. When the valve is fully open, the flow capacity would be maximum. So the flow capacity of control valve is determined by its capacity factor or flow coefficient, which is CV. So this one you already see inside the previous topic, right? The CV value. Okay, so this CV value, I would like to introduce about the CV. So basically, it's the flow in US gallon per minute that flow through a valve at a pressure drop of 1 psi across the valve. Okay, so for example, like valve with CV of 25 can deliver 25 gallon per minute of water when it has a 1 psi pressure drop. Okay, so for the flow through the valve, we have liquid. So for the liquid, we will use this formula to calculate the flow. This is flow, this is the flow coefficient, delta PV, which is the pressure drop across the valve, and also the specific gravity. Okay, so like what I mentioned inside the previous topic, subtopic, we have W, right, which is mass flow rate. So this W, we can calculate using this formula. Okay, so the unit is pound per hour. So to simplify from this one, we get this formula. So if you have the information of delta PV and also specific gravity and CV, you can calculate the mass flow rate. Okay, so now we try to do one example on how to use the flow equation. Okay, so let's read the equation, the question first. So from figure this one lah, a 3-inch Masonite valve with full trim has a capacity factor of 110 gallon per minute over psi when fully open. So the pressure drop across the valve is 10 psi. So we need to calculate the flow of liquid solution with density 0.8. So the density of water, this one is in gram per centimeter per cube. Normally we have kg per meter cube. So in gram over cm meter cube, the density of water is 1. Okay, so from this table, this figure, okay, we can read the value of capacity factor. So given in here is 3-inch valve with a full trim. So this is a full trim. So you have a 3-inch valve. So you can see here, this is half, 1.5, 2, 3. So basically this is 3-inch. So okay, so to get the capacity factor, we also need to see at this column, which is we need to get the 3-inch valve also. Okay, so after we read from the Y column and X column, we will get 110 capacity factor. So now we calculate the value of flow of liquid. So the value of CV would be 110. So the delta PV would be 10. So the specific gravity would be 0.8. So the final answer of the flow of liquid solution would be 383 8.9 gallon per minute. Okay, so this one lah. So if you want to convert this one, the flow of the liquid solution into the mass flow rate, you may use the formula of 500 CV GF delta PV. So you will get this value. Okay, so for the liquid services, basically we will use this formula like what I mentioned before. So this formula also equivalent to this one, which is Q equal to CV cert times cert delta P over specific gravity. Okay, right now we gonna calculate the CV of a control valve when a 480 gallon per minute fluid having a specific gravity 0.85 pass through it. So the pressure drop is 15 psi. So you can see here the pressure drop is basically the pressure across the valve. So if you see inside your lab, you can see that before the valve and after the valve there is a indicator. For example, like this one is flow indicator. So this one is to read the flow rate, and sometimes we have a pressure gauge. So for the pressure gauge, we want to read the pressure at the inlet and the outlet of the valve. So we need to calculate the CV. So the flow here is, we use this formula CV delta PV over GF. So this F is 480, CV is the unknown, this is 15 and 0.85. So the last answer would be 114.263 GPM PSI. Okay, for the compressible flow, which is gas or vapor, okay, we can use this the equation of gas or vapor flow, which is Fs. Okay, so this Fs, the unit is cubic feet per hour, and the standard condition is 14.7 psia and 60 degree Fahrenheit. Okay, for the gas specific gravity, basically we refer to the air density. So basically the value of the gas that been given, the molecular weight of the gas should divided with 29. Okay, 29 is the average molecular weight of air. Okay, for the temperature, so this one inside the formula, that means this G, you need to make sure that you divide it by 29 if you get the molecular weight. Okay, for the temperature in here, basically the temperature at the valve inlet, the unit is Rankine. So if you get the value Fahrenheit, you need to change by plus with 460. Okay, for the critical flow factor here, CF, normally we will choose between 0.6 to 0.95. So inside the question normally been given lah. So basically this range is depend on the valve type. For the P1 here, okay, the pressure at the valve inlet is in psia. So if you get the pressure in PSIG, you need to change by plus with 14.7 psia in order to get the psia value. Okay, so for the Y term inside this formula, you need to calculate using this formula, which is 1.63 over CF square root delta PV over P1. So normally delta PV been given inside the question. The value of P1 also you can obtain from the question, and normally this value of P1 is in PSIG, so you need to convert by plus with 14.7 in order to convert to PSIE. Okay, so now let's try to do this example. Okay, we have a 3-inch Masonilan valve with full trim. Okay, basically the same valve as we do in question 1. Okay, has a capacity factor which is 110 when fully open. The pressure drop is 10 psi. Calculate the flow of the gas with average molecular weight 35 and the valve inlet condition are 100 psig. This one is P1. So the temperature would be 100 Fahrenheit. Okay, so before we calculate using the formula of gas flow, we need to calculate the Y, the value of Y. Okay, so you just insert the information, which is this one is a CF, this one is a P1, and this one is a delta, the pressure drop delta P. Okay, but you need to, at first, each of the information that been given, you need to confirm it, because as you see the definition of each of the term inside the gas flow. Okay, for example, like the value of G. Okay, normally the gas, the standard reference gas, we will refer to this one, which is 29. You need to change first the specific gravity, and P1 also, because this P1 is in PSIA, the value that we get is 100 psig. So you need to plus with 14.7 in order to get the PSIA. This one. For the temperature, because you need to use the Rankine unit, so from the 100 Fahrenheit you need to change to Rankine, which is plus with 460. You get this one. Okay, so after you get the value of Y, okay, you can substitute all the unknown inside the Fs. So this one is for CV, and you may check back the formula inside the previous slide. This one it's a CF. Okay, so this is the specific gravity, GF. This is temperature. This is a P1. Okay, this is the value of Y. Y minus 0.148Y to the power of 3. So your Fs would be 187,000. Okay. Okay, now we move to the sizing of control valve. So sizing control valve for liquid service, there is a 3 criteria that need to be fulfilled, which is flow through the valve, pressure drop across the valve. This one, there is a 3 criteria that need to be considered. Lastly is specific gravity of the liquid. So this is the sizing control valve for liquid services. Remember the formula that we learned previously, which is F equal to CV delta PV over GF. So for the control valve for compressible flow, we refer to Fs. So that Fs we need to consider the flow through the valve, pressure drop across the valve, specific gravity, inlet pressure and temperature, and average molecular weight of the fluid. Okay, for sizing the valve, use the information to calculate the CV coefficients. Once the CV coefficient is known, select a valve that is large enough for the services. Okay, remember inside the figure, the first figure that we see before. Okay, after you calculate the CV, you may refer to that table. You can see the size of the valve that's suitable for you. So that one we call it as a sizing. So if the value of CV is large enough for the services, okay, normally we will select the valve that have large enough capacity to sustain the CV coefficients. Okay, so generally the calculated CV falls between two different valve size. So if you get the value of CV is in between two valve size, you may select the larger valve. So the capacity factor would be, the formula would be like this. Basically, we rearrange the previous formula, the flow of the solution, liquid solution. Okay, the valve coefficient must be greater than the one calculated from the equation. Normally, the real valve coefficient must be greater than one that been calculated. So that's why we need to pick the large size if the CV fall between two range. Okay, the ratio of the valve coefficient when the valve is fully open to the valve coefficient at nominal flow is equal to over capacity factor of the valve. That means the CV max over CV is a over capacity factor. So for the over capacity factor equal to 50%, the factor would be 1.5. If over capacity factor is 100%, the factor would be 2. Okay, so now we try to do this example. Okay, we read the question first. Okay, a control valve is to regulate the flow of steam into distillation column reboiler with a design nominal flow of 16,100. The supply steam is saturated at 20 psig. Size the control valve for pressure drop 5 psi and 100% over capacity. Okay, so let's see the solution. Okay, basically the given pressure is 20 psig. First we need to identify what type of fluid that being used. Inside the question mentioned the vapor, right? So that's why we use the FS formula. Okay, to solve this FS formula, there is a few criteria need to be confirmed first. Need to change the units before we insert inside the formula. Okay, so the first term is valve pressure. We change to PSIA by plus with 14.7. So the molecular weight of the stream would be 18. Given is 18. So the specific gravity, okay, because we refer to the standard which is 29, we just divided 18 with 29, we get this one. We assume that the CF is 0.8. So why we can obtain? Because we have the all the value given. So we can get the value of y and then rightly calculate the y minus 0.148 y to the power of 3. So this one basically been used inside the FS formula. Okay, so just now we get the information of the mass flow rate, so we need to convert it into a flow of liquid solutions. So how to convert? Basically, you need to time this one, time with the molecular weight, and time with this one. Lastly, you will get this value, which is 340,000. Okay, you may refer this formula inside the slide of flow, the slide that shows the equation of flow of the gas. So the unknown inside the Fs formula just now is CV, so we rearrange the equation and we will obtain the last value of CV is 440. So mentioned inside the question, the overcapacity is 100%. So we can use the factor 2 to calculate the CV max. So the CV max, you just time with 440, we will get 880 gallon per minute over cert PSI. Okay. So after we get the maximum CV, from that we can identify what type of size of the valve that may use. Okay, we can see from this table, the value of 880 is in between here. Okay, so basically is in between. This is the last term and this is the last term of each size. So the last term for the 8-inch is 680, for the 10-inch is 1000. So it's fall in between. So like what I mentioned before, if it's fall in between, we need to choose the largest size, which is 10-inch. Okay, now I would like to show you on how to solve this exercise. So basically, control valve is used to regulate the flow of steam. The nominal flow of the steam is 180,000 standard cubic feet per hour. The valve condition are 100 psig and the temperature is 60 Fahrenheit. Pressure drop is 5 psig. Size the control valve for 100% over capacity. The given steam molecular weight is 18 and the critical flow is 0.8. Okay, now we start with convert all the properties units. T, we convert to Rankine, which is we need to plus 60 Fahrenheit with 460 is equal to 520 Rankine. So for P1, okay, the valve condition is 100 psig, so you need to plus with 14.7. The answer would be 114.7 psie. Okay, so next is specific gravity G. So you need to divide it by the standard molecular weight, which is the standard molecular weight of air, 29. You get 0.621. Okay, so you can solve the y first. Y, the formula is 1.63 over CF, which is 0.8 time with square root delta PV over P1. Okay, the answer would be 0.19997. Okay, next y minus with 0.148. Basically, you can calculate directly or you can insert inside your main formula. This one is 1.986. Okay, so to calculate the CV, basically you use the gas flow formula, then you rearrange back. So this is the flow, the gas flow, time with square root G, which is 0.621, time with temperature 520, over with 836, time with 0.8, which is our CF, time with P1 114.7, time with Y, Y minus 0.14, Y to the power of 3. So I already calculated, so I just write the value. So the answer for CV is 212.315. Since the mention here is 100% over capacity, that means CV max, you need to time this value with a factor of 2. So you will get 424.63 GPM PSI. Don't forget to write down the unit. So for this one, GPM PSI. Okay, so we can see that the value of CV max is around 424. Okay, so we do a sizing. Okay, we can see that the value is in between 400 and 640. So we choose the largest size, which is 8 inch. Okay. Okay, so now I would like to highlight the issue on control valve. What make a control valve become linear, equal percentage, or quick opening control? So why flashing and cavitation are serious problem in control valve? What causing flashing and cavitation in a control valve? So this is the 3 most highlighted issue on a control valve. Okay, make sure you know about that one. So basically for the first issue, which is what made a control valve become linear and equal percentage or quick opening. So basically it's depend on the amount of the flow produced with respect to the steady increment in the stem travel. So basically this one lah. This is the stem. So the amount of flow produced when this stem is moving, what is the amount of the flow is produced. So from that one, basically we come up with linear, equal percentage, and also quick opening. Okay, why flashing and cavitation are serious problem in control valve? Because it can cause erosions. You can see from this figure, this is erosion. Okay, so what causes flashing and cavitation in control valve? So basically flashing occur when the pressure of the liquid fall below its vapor pressure. So most of the liquid will change the phase to the vapor pressure. Sorry, change to vapor phase. So that's mean inside the flow, the liquid is not uniformly liquid. There is a vapor phase inside the liquid phase. So cavitation is it's happened when the pressure recovery experienced by the liquid is enough to raise the pressure above the vapor pressure of the liquid. So when the pressure of the liquid raised above the vapor pressure, that means the vapor bubble will start to collapsing. So that means inside the valve will have a bubble. So that bubble basically can cause the pressure drop and cause the noise of the valve, cause the valve become unstable. You can see this is the bubble, cavitation bubble. So basically it's formed at the surface, fixed surface. This bubble will generate a jet of surrounding liquid. You can see the bubble inside this valve. So this bubble, it can cause, it will affect the movement of the stem also. Okay, so I think that's all for this topic. If you have any confusion or you want to ask me, you can PM me. Thank you.